So now we want to prove this theorem, and in order to do that, we will use this characterization of this row function. So how we are going to do is we will use induction. Induction on n, the dimension. So for the base case, if n is 1, then it's easy because this is 1 or 0 depending on whether A contains X or not. So if you want to compute this integral, then you just take the measure of A give me a moment. And with probability, so if this is 0, then exponential of this is 1. That happens with the probability A. And with the remaining probability, this is 1, so if you put it, then it's e to the 1/4. Then we can actually check that this is at most 1 over probability of A. Because for u between, say, 0 and 1, positive number u, we can actually check this inequality. So we can check that this holds for base case. So now we use induction. Assume that we have the result for n. And we consider omega, which is the product of W1 to W sub n plus 1. And let's say we take the omega superscript n to be the product of first n, omegas I. Then what do we want to do? We want to consider a point, and we want to distinguish the last point, last coordinate, and then we consider this coordinate and this coordinate. And then we want to kind of project the point onto the first n coordinate, so to this space. And then from there we use induction so that we can conclude on the original space in here. That's roughly what we want to do. Then for any points in this omega, it can be uniquely written as, say, x comma w, with x being the points lying in the first n coordinate, and w is the last one coordinate. So let B be the projection of A into the A superscript n, and for each w, let A sub w be the first n coordinate together with W lies inside of A. It's if you take the slice of fixing the last coordinate, then you get the with that hyperplane, you take the intersection with A, then what you get is AW. So, for example, if you have, say, this is A, then let's say this is the last coordinate, x1, x2, then this is B. On the other hand, so each of them are just, let's assume it's in R. If we have a W here, on the, so this is B. You project it to the, first n coordinate. If you have W, then this, you take this and then you project it to here, then that's A sub W. Then what do we know? Now we want to analyze how U, B, X and how A, W, X are. So what we want to do is we want to express this in terms of rho Bx and rho AWx, depending on, so here, this is integral over omega, which is integral over first n coordinate and then last coordinate. This last coordinate actually gives this W. So somehow we want to relate this with these two by changing some, integral somehow, or splitting integral if necessary or something. So that's roughly what we want to do. So for that, we know the characterization of this rho in terms of this V. And this V is convex combination, convex hull of U. So we need to kind of analyze what properties we have on this U. So what we know is if S is a point in this U, B, then we know that in the larger space, omega, in the original space, omega n plus 1. So this is omega in omega n. If we add 1 at the last coordinate, then it's in this U. So meaning that if you have a point, give me a moment. Yeah. So this is here, meaning that in B, there are some points Y. So in that case, give me a moment. Yeah. This is in here, meaning that if you have S, then there exists Y in B, which differs from X on, which is same with X on these 4 points, these 4 coordinates, and possibly different from X on these 4 coordinates. It could be same with one of them, but as a subset of this. And if you put 1 at the last, then that kind of indicates that we don't care whether, this is image. So B is the projection of A. So this is in here, meaning that there exists a Y prime in A, which projects into Y, which means that its first n coordinate is same as Y, and then last coordinate could be anything. So it could be same with W or it could be different with W. So we just add 1, then we know for sure that's in here. S, 0 might be there or might not be there, but we surely know that if we add 1 at the last coordinate, it is there. So C, this is the reason why we actually define U in the previous way, by allowing only this one direction, not the other way direction. And if S is in A sub W, X, then we know that if you append 0 at the last coordinate, then it's in the U set of this A, X, W, X, W here. So now we know this. So now we know about this and this. So, but what do we want to analyze? We want to analyze this. And we want to find a V in here with a minimum size, which will yield low of A, X, W. That's what we want to measure. When for given X and W, we want to measure this, and then we want to take the integral over all XW there. But we know this V, A, XW is a convex combination of these vectors. So, what we know is that, let's say this is T. So we take a vector X, S and T from here and here, then we know that these lies in U. Then for any lambda between 0 and 1, what we have is, if you take 1 minus lambda times S plus lambda T, you take the convex combination of these two, 1 minus lambda is in V of A, XW. So now what we want to do, we want to find an upper bound on here. So all we want to do is find the upper bound here. Here we have equality, but what we actually need is just upper bound. So if we take 1 point in V, then that already gives us upper bound. But they might not be as good. They might not give as good upper bound as we want, but it gives us one upper bound anyway. So this 1 point already gives us an upper bound, and we want to kind of optimize the upper bound by choosing this lambda wisely. That's roughly our plan. So by the previous theorem, what we have is the low scale A XW is when XW is arbitrary 1. Then this is, you take this vector and then take the summation of the coordinate, and then you add the last coordinate square, which is at most this plus this plus this. But again, what was S and T? This is true for all S and T inside of this U and inside of this U. So we can also choose them to make sure that this is as small as possible so that we can get a better upper bound. So we choose S and T satisfying these. We know that give me a moment. Let me briefly check. Okay, I have wrote one thing wrong. Yeah. So, I forgot to write one thing here. Oh, sorry. So, I forgot to explain one step. From here, what do we know? We want to, say, take some point S arbitrarily in V, now say. So instead of U, we take S from V. Then, again, this is in V of A, XW. And T is in V, AWX. Then, again, T0 is in V, A, XW. We know this, right? Because if this is in here and this is in here, and if S is in here, that means S is a convex combination of several S1 and S2 and S3 in here. And by this, we know that S1, 1, S2, 1, S3, 1 are all in this U of A, XW. So their convex combination, again, give us this. So we know this. And for that, now we know for given lambda, we have this. So S and T, any vector S and T from V, V of B and V of AW, this is hold. So we can actually choose them to satisfy that its size, its norm, is same as the rho of B and rho of AW. This is from the previous theorem. There exists one vector whose norm is same as this distance that we are measuring. So then what does this become? This become rho square of A XW is at most 1 minus lambda square plus lambda times rho square AWX plus 1 minus lambda times rho square PX. So now we have this. So this is a relation we have. So this is the kind of quantity that we want to measure. We want to take the exponential and then take the integral. But this is what we want to measure. And these are the upper bound. And then each of these are something that we can already measure. It's in the lower dimension. So now what we do is we first fix what? Fix W in the last coordinate. And then what we have, if we take integral over x for fixed W, and this can be upper bounded by using this. Constant term, because we take the exponential, this becomes constant term, which is multiplicative constant term, and rest of them becomes this times this to the lambda times exponential 1 minus lambda. So this constant multiplied becomes exponent here because we take the exponential function. Now if we have a integral and then you multiply it with this power, then there is inequality that we can use, Helder's inequality. Use that this is at most. You can divide the integral into these two. We get this. But now this is the integral with one lower dimension, so we use the induction hypothesis. Then this is measure of this AW in a lower dimension, dimension n. And this is the measure of B. And let's just write it this way. Times, say 1 over r to the lambda, where r is the ratio between AW and B. So AW is a subset of B. That's obvious from its definition. So this is something most 1. Now we want to choose lambda to optimize, and that optimization is actually related to this R. We choose lambda to be 1 plus A2 log R if R is bigger than e to the half square root of 1 over square root of e, and 0 otherwise. So this is just to optimize the expression. And by using some calculations, we can check that this actually is at most 2 minus r with this choice of lambda. Then what we have is that this integral is at most 1 over probability of b minus 2 minus r, so r is here. R is this ratio between the measure of a sub w and measure of b. Now what we do is we integrate over w. So this is integral over the first n coordinate, and then this is the last coordinate. And what do we get is w of this probability of b 2 minus. So b is fixed, and over this w, this changes, but what's the probability of AW? So the measure of AW, and you take the integral over w, this is exactly the measure of A. Because each of w, A sub w is a section. You take the hyperplane, which is obtained by fixing the last coordinate to be w, and you take the section, you take the intersection with that hyperplane and A, then that's exactly this 8w, and then you take the integration over the choice of w, then that yields the measure of A. So this is what we get. And by letting x be the ratio between the probability of A and probability of B, note that this is also between 0 and 1. Because B is how you get by taking projection into first n coordinate. So this is same as, this is in nth dimension and this is in n plus 1th dimension. So in here, no, in here and here are same as you take B by the last one. This actually contains A, so this is bigger than or equal to the measure of A. So by taking this x, what does this become? This become 1 over say measure of A times x, 2 minus x. This is 2x minus x squared plus 1 minus 1. This is minus 1 plus, minus 1 plus 1. This is 1 minus x squared, which is m of 1. So we get the desired upper bound. So this completes the induction step and then proves the theorem. Now we have this. So this integral is same with this expectation, and you apply that, then you have this is at most this. So you multiply this on both sides, then you get the Lagrange inequality. So now we have a Lagrange inequality as we want. Now we will consider an application of this in the next video.